Hello, this is Professor Keen. I've been talking about Proposition 4, Theorem 4 in Book 3 of Newton's Principia. I think my last lecture was pretty difficult. Probably you had trouble following this because I went through some of the details of Newton's proof. So let me just kind of highlight what some of the important points were that Newton was making. Remember, the idea here was that Newton was trying to argue that the exact same force which holds the moon in its orbit around the Earth is the force that causes objects to fall near the surface of the Earth. Okay, so remember the idea here is that I've drawn here this brown circle, imagine that to be the Earth. This big blue circle is the orbit of the moon around the Earth in its ordinary orbit, and it is a distance of 60 Earth radii. So if this little green line here is the Earth's radius, this is 60 times Earth's radius away from the Earth. That's how far away the moon is in its approximately circular orbit. While it's orbiting, it is feeling a centripetal force. So there's a centripetal force pulling it in. Okay? And we found that the distance that the moon would fall equals the distance fallen. Let me use a different pen. X equals the distance fallen by the moon in 1 minute due to this centripetal force was equal to 15 and 1/12 of a foot. And he used his proposition 4 corollary 9 to figure that out. Then what Newton did was said, okay, let's hypothetically imagine that the moon, instead of orbiting out here, there was another moon. So we'll call this moon 1, and we'll call this moon 2, or maybe moon prime, a new moon, a special new moon, okay? And if it was orbiting not at 60 Earth radii, but at 1 Earth radius, I know this isn't exactly 1 Earth radius, but at 1 Earth radius, how far would we expect it to fall during 1 minute? Well, he argued that because it is 60 times closer, if the centripetal force is a 1 over r squared kind of force, that is the force holding it in orbit is a 1 over r squared kind of force, if you're 60 times closer, then it should be not 60 times stronger, but 3,600 times stronger, or 60 squared times stronger, because after all, it's a 1 over r squared kind of force. So on this new moon, the force would be 3,600, or 60 squared times bigger. Because the force is 60 squared times bigger, the acceleration it feels is 60 squared times bigger. And so the distance it falls would be 60 squared times as big as 15 and 1/12 feet. So it'd be a much bigger distance that it falls. But he said, let's suppose we were to figure out x prime, the distance it falls not in 1 minute, but in 1 second. That would be 1/2 of this new acceleration times this new time squared. And because the acceleration is 60 squared times bigger, but the time was 60 and then squared times smaller, this new distance that it falls, x prime, was going to be the same as the distance this moon falls in 1 minute. In other words, the distance this moon would fall in 1 second would be the same as the distance this moon falls in 1 minute. That is 15 and 1/12 feet. And this is predicated on the idea that there must be a 1 over r squared kind of force pulling the moon in. That's a summary of where we were last time. Now, why is this important? Because it just so happens that experiments demonstrate that falling objects near Earth's surface fall just about 15 and 1/12 feet in 1 second. This is actually a stunning result. He says, therefore, and this, by the way, these were measured by Christian Huygens, a very famous Dutch scientist that we study in Physics 202. He used pendulums to measure this to high precision. So what does Newton conclude here? He concludes that whatever force, therefore, whatever force keeps the moon in its orbit, at this very long distance, if it increased, or it changed, it varied as 1 over r squared, if it's a 1 over r squared force, as one gets closer to Earth, as you move the moon or whatever object closer to Earth, this makes things like moons fall at the same rate, as dropped objects as measured on Earth or near the surface of the Earth. This is a stunning conclusion. It is a link between the force holding the moon in its orbit and the force that is causing objects to fall near the surface of the Earth. This is the key insight that Newton has. This probably takes a couple times of going through to understand the significance of this. So what Newton does is in the very next page, he provides a scholium, which attempts to try to present this in a slightly different way. Okay? So let's spend a minute going through this scholium. Okay? So he says, let's consider it this way. This is another way of understanding this. If the Earth had several moons, so consider that possibility. The Earth had several moons, more than one moon. If that, then these moons would obey Kepler's third law. That is, their orbital times would be related to their distances from the Earth to the 3/2 power. How do we know this? Well, he says by rule 4, his fourth rule of reasoning, that is the principle of induction. So this is a different argument than the previous argument. He's saying, well, we can look at all the moons, the multiple moons of Jupiter, and they obey Kepler's third law. The multiple moons of Saturn, they obey Kepler's third law. The planets orbiting the sun, they obey Kepler's third law. So if the Earth had several moons, let's assume this is a general principle, and those moons would obey Kepler's third law. So if you had the Earth right here, and you had several different moons orbiting the Earth at different radii, then by rule 4, or the principle of induction, by looking at all the other planets and moons, those moons of the Earth, moon 1, 2, and 3, and however many we want, those would all obey Kepler's third law as well. Okay, where does he go from here? He says if Earth's purported moons, obey Kepler's third law of planetary motion, then the force holding them in their orbit, so if that's the case, then the centripetal force holding them in orbit would be a 1 over r squared, or inverse squared law acting on the moons. How do we know this? My pad is freezing up here on moons. We would know this by book 3, proposition 1. That is anything, I'm sorry, did I get that right? I think, maybe it's book, yeah, I don't remember which one this is. So let me put a question mark here. But if something obeys Kepler's third law, then there's a 1 over r squared force that is acting on it. This is actually book 1, proposition 4. Book 1, proposition 4, corollary 6. That's right. Okay. All right, good so far. Now, he says, if the lowest of these moons, or the nearest of these moons, let me get rid of this. If the nearest of these moons orbited just above the Earth's surface, just above Earth's surface. It's a hypothetical situation where this one is just skimming right over Earth's surface, right near the tallest mountain. So here's mountains. I know this is kind of a silly drawing. It's skimming right above the Earth's mountains. If that was the case, then what? Then the force with which the Earth pulls on it would give it a weight equal to the weight of similarly sized earthly objects. Then the force with which Earth pulls on it would translate into, or give it, a weight. After all, a weight is just a force. Give it a weight equal to the weight of typical terrestrial or earthly objects instead of lunar objects. That's what he showed in this previous postulate right here. You have a closer distance, 1 over r squared force. The force goes up. It's going to give it a similar weight to those objects. And if, he says, the weight was the same as a terrestrial object, if the weight was the same as a terrestrial object like a rock, then it would descend with the same speed as a dropped object. If deprived of its orbital motion. It would descend with the same speed as a terrestrial object. If deprived of its orbital motion. Okay? And now he goes on to say, but if the force which causes this little moon, this moon number 1, to fall were different, or from some different source than the force that causes terrestrial or ordinary bodies to fall, then you would also have the force which causes ordinary terrestrial bodies to fall. That would be sort of supplementing this other force, and would fall twice as fast, which it does not. So if the force which causes the little moon to fall causes this nearby moon to fall were different, and by different I mean from a different source. From a different source. Then the force causing terrestrial objects to fall then it would be supplemented would be supplemented by whatever force causes regular objects to fall. Whatever different force causes ordinary or terrestrial objects to fall. And so it would fall twice as fast. But, of course, it does not. It does not fall twice as fast. So he says by rule 1 and 2, that is, to same effects one should attribute the same causes. So by his rules of reasoning, rule 1 and 2, these are the same force. They are in fact the same force. Again, this is a little bit of a tricky argument, but essentially he's saying if you imagine there is some distinct force that is causing these moons to orbit the Earth, and you predict how fast these objects would fall near the surface of the Earth due to this new special force, you would find that they fall at the same speed as normal earthly objects fall. But if that's, like I said, a new or different force than the ordinary force that causes earthly objects to fall, then you would need to supplement this new force with that ordinary terrestrial force, and those objects would fall twice as fast. Which seems to be strange. That wouldn't be quite right. So he says, if you get the same effect, that is falling at 15 1/12 feet in 1 second, due to the terrestrial force, and 15 1/12 feet due to this centripetal force acting on the moons, the effects are the same, so why aren't we just saying the causes are the same? This is rule 1 and rule 2 in his rules of reasoning. And so we can identify the force holding the moon in orbit and the force causing, for example, apples to fall. And that is the highlight of Newton's Principia. That is how he develops his universal law of gravitation. In my final lecture next time, what I will do is just write this law of gravitation in its modern form and work out 1 or 2 problems.